All right, so the goal of this video, well, I guess not this video, but this sort of series of videos is to be able to find an expression for the derivative of sine and cosine. And sort of if you think about this, I mean, what's ultimately going on is these functions could be viewed visually, graphically. If you did, you may recall that these functions are periodic functions moving up and down, undulating between values of 1 and -1. But the long story short is these curves could be viewed, zoomed in on any point, and if you did zoom in on any point, you would get a line. That line would be the tangent line. That tangent line would have a slope. So we're going to work to try to find an expression for the slopes of the tangent lines to the sine function and the slopes of the tangent lines to the cosine function. Now to do this, there's going to be some technical details involved, and some of the technical details relate to what is currently written up here on the board. So first off, let's just recall something. This is from trigonometry. This is nothing fancy. This is purely a formula, just grabbing the formula for angle sum related to sine and related to cosine. So the sine of the sum of two angles is the sine of the first angle, cosine of the second, plus cosine of the first, sine of the second. That is just the formula that it is. Pulled again straight out of a trig book. Cosine A plus B, something also that you've seen before, probably memorized for a test back in the day. Long story short, cosine A, cosine B minus sine A, sine B. You'll never have to know these for our purposes, other than just to apply them whenever we compute the derivative and go through the details. These next two are limits. I believe we actually encountered these limits through activities in class back in the day, but hey, long story short is, let's just sort of remind ourselves of what's going on with these limits, or let's just sort of take a look at what's going on with these limits based on what we can see. Here, the first is the limit as h approaches 0 of cosine h minus 1 over h. You know, one way that you can sort of like naively try to get a feel for the limit is by just plugging in h values that approach 0, or well, approach whatever your h is approaching, from the right, from the left. So approach 0 from the right, you'd have h values like 0.1 or 0.01 or 0.001, and you actually see what's happening to cosine h minus 1 over h as you plug in those h values. The closer the h's get to 0, the closer the outputs get to 0. 0.0005 is very, very close to 0. From the negatives, when you let h approach 0 from the left, you would have what h's of like minus 0.1, minus 0.001, minus 0.001. Start plugging these values into our function. We get out things that, again, approach 0. So from the right, we approach 0. From the left, we approach 0. Well, then, the approach is 0. Okay, that takes care of this first limit of interest. What about the second limit of interest? The second limit of interest is sine h over h as h approaches 0. So, well, if we want h to approach 0, want to get a feel for the limit, let's just start plugging in values for h. So like 0.1 or 0.01 or 0.001, and you see what's happening here. The values are like 0.99999. That is really, really close to 1. It feels like the limit is 1 from the right, and from the left, negative 0.1, negative 0.01, negative 0.001, you again get 0.99999, which is almost 1. So the limit from the left approaches 1, the limit from the right approaches 1, so the limit is 1. And well, with that in mind, we're sort of ready to step forward into